also mentioned is the 3D filament that we're using for housing, and then some lenses that we've experimented with. So to put it all together, we created a drawing in SolidWorks and then printed it on 3D printing, and then manually soldered all the electrical components, and then manually assembled all the internal mechanical and optical components. And this is just an overview of basically the entire system. It's all held within this housing, which is a safety feature to prevent the user from electric shock and shortages. I'm not really going to go through all of this because we kind of just went through it, but basically what is happening is our system is emitting an excitation light to whatever the target sample is, and then we're capturing the fluorescent signal selectively with our bandpass filters, and then that signal goes to the CMOS sensor and back to our computer, where the Wi-Fi signal then displays it onto a smartphone. This is the first prototype that we created. It's basically an exploded prototype. No housing here. We just wanted to prove that our concepts were legit and they would actually work like we intended them to. And then on the right is our model for cellular imaging, where we have a microscope attachment to the device. And these are our first proof of concept results. We basically just wanted to make sure that what we thought would work did work. And so you can see that the colors that we were able to achieve correlate well with the literature that we compared our results with. And so we wanted to make it mobile as well. Sorry you cannot see the text here, but I pretty much already kind of went through that in the system overview. It's just showing the electrical components, how they're connected, and then the wireless transmission. And then this is just kind of the layout of making it mobile here, adding the battery, the charging unit, on-off switch, and then some of the geometries of lights and other light sources that we've tried look something like this. These are high-powered LEDs, different ranges of wattages. We were trying to experiment and see how the wattage would allow for deeper penetration. And these were some of our filter ideas. The scroll wheel here was an idea that we had if we were to incorporate a small amount of LEDs in our array. And then this linear sliding filter was for an idea that we had if we were to incorporate a large amount of LEDs to the final design. So basically the differences here depend on our spatial arrangement of our other components. And so to really figure out what components and LEDs were important, we created this temporary filter clip-on. Thank you, Dr. Hawkins. We had these clip-ons because we wanted to experiment with what bandpass filters would work best, and we wanted to make the device able to image many of the popular biomarkers such as GFP and fluorescein. And so this is our new prototype with the filter clip, and we're imaging a sample of ICG here and displaying it on the computer just for presentation purposes.
So after we developed this new current model, we wanted to verify our design and make sure that things would work. So just the other night, Kyle and I stayed up until 8 in the morning finalizing our new design. And on the left here we have, or on the right here we have a vein visualization experiment. In the middle we have an ICG sample at a concentration that you would inject into the body and then try to image through that using other technology that exists now. And so we just kind of wanted to see if we could image in the NIR just through a simulated type vein. All the way on the left, we put a piece of just Angus steak on top, about a little more than ½ centimeter in thickness, and we were successfully able to image through it, which was what we set out to do from the start, being able to use the NIR biomarkers in order to image through through tissue. So this is just another close-up example. We have video. A little scared to use it right now, so if any of you want to see it after the presentation, we have it on our own devices. And so in terms of doing statistical analysis of it, since we just got our results, we want to fine-tune what we can do. The other night when we were finishing this up, we were using one 3-watt LED at 2.5 volts of energy, or just power, and that is nowhere near what we can run. So by over the summer, we want to figure out the best setup we can have, and then we'll hopefully be able to image through at least 1 centimeter or 2 of steak, which is a very ambitious goal, but we'd like to do that by the end of summer. What we eventually want to do is figure out, we want to test our device versus the EBOS microscopes or other type of current imaging tools, and we want to do it by just doing a two-way analysis of how much area we can actually detect through the amounts, through varying amounts of steak. And we would use statistical software, JMP, Photoshop, and ImageJ in order to conduct these analysis.
So our future work here, we'd like to image or test our platform while imaging mice. We will need to get SJSU approval before we can do that, of course. We'd also like to continue our development of the iOS and Android platforms, so that it's just more user-friendly to whatever cell phone the user has. Also, we'd like to be able to start streaming and storing the images on one of these storage programs such as Dropbox, LabVIEW, and Google Docs. And then further in the future, human clinical trials where we will be needing IRB and FDA approval for that. And then hopefully cancer imaging. We'd like to see if we can image cancer within the lymph nodes. And then once all this has been successful, we'd like to start a company around this. And we would be calling ourselves Mantis Medical Imaging after this shrimp here who is able to see in a wider range of the electromagnetic spectrum than humans can. And they actually fluoresce during mating, so it's a little creature that packs a punch, and we figured that it represents our device and our goals very well. And one thing that we're most excited about actually is being able to use our device in clinical trials at the Cardiovascular Innovation Institute with Dr. Stuart Williams. He actually approached us at the BMES conference asking to actually write a IRB protocol for us so that he could get our device into his clinic, where he would like to image the palms of patients who had recently or immediately after having total hand transplant surgery. And he would use that to make sure that the sutured veins are fully connected and there's no leakage after transplantation.
So just to wrap it up, we're going to look at local and global impacts. So locally, we want to help out students like Jose. These are actually his quantum dots. He's very happy about them. Thumbs up. Likes this idea. I don't know if Jose's here, but he likes our device. So that's a local impact. We want to help people who can't necessarily afford the big machines that exist at bigger universities. Global impact, we'd like to be able to use this as a tool for diagnosis in third world countries. We think that this could be used in the field for fluorescence research just out and about, and you can send things back to the lab just through sending an email. We We want this to be an affordable tool for aspiring scientists and people who are young. You know, we're hoping to make this cost around $100, so it'd be great for them. And we want this to maybe eventually be a handheld device that can be used for, like, by doctors during surgeries. So I'd like to thank Dr. Eric Bogbo, our technical advisor, Craig Bruns, our industry mentor, and Will Rye, our graphic designer, as well as the corporations and funding places that helped fund our project and are helping us make this project work. These are our references. Thank you again for being here.
We have a little time for some questions. Anybody has questions or comments? Yes.
So your quantum dots are functionalized?
So we're not making the quantum dots. That would be Jose's group, but they're working on functionalizing them right now.
Okay, so how are you testing the affinity of your quantum dots to tissue, and then how are you? And I'm also curious about the imaging side. Are you pulling data from directly from the pixel, and if so, how do you overcome the filtering technology that are embedded in the imaging devices?
So for the first question, we are imaging just ICG because we can put it in solution, just image it right now through tissue at the moment. Jose is currently functionalizing his cells too. I forget what type of cells, but we will work with him on functionalizing it in the tissue samples that he wants to use. For the second question, are you asking about the deconvolution process of?
I'm just curious on how you pull data from your device.
We had to
And-
alter
and-
the images
and
because
you have to bypass the embedded filtering that these devices have.
The reason we actually chose the particular CMOS sensor that we showed you was because it's unfiltered, and therefore we're able to decide what filter we want to incorporate.
Okay, so then you're actually saying smartphone, but you're talking about a device that looks like a smartphone that's specifically tailored for your application.
Yeah, the smartphone was only to be used as our user interface, so that we just figured that it would be easier for the user if they could.
we tried to solve them, but taking out that NIR filter is real.
Oh, it's a bear.
Anybody else?
Yes. Did you guys get the wireless to work, or is that more for future?
Yeah, no, we have the wireless working. We showed it on a computer just because we were able to get that image with our sample and our device there, and then it was just a convenient way to show what the device was detecting.
One of the advantages of the Raspberry Pi is that the software is a lot of it's open source, and it's been very helpful to actually doing that aspect of our project. So we were able to get it onto actually Kyle's cell phone multiple times.
So you excitate the quantum dot using an LED, is that it?
A specific LED with
Yeah,
specific wavelengths.
so I'm curious, in what size quantum dot were you able to image? The smallest quantum dot size that you were able to image?
We can't really say what the
You made a
smallest-
dot, right?
Yeah, I mean,
So currently, Jose's quantum dots that we imaged were just, he hasn't been able to sort out the sizes yet, so we just kind of took a grouping of them. There's a whole bunch of different ranges, so we are gonna eventually try and buy them, but quantum dots are very expensive, and that's been one of the issues as well, just being able to afford them.
our whole goal too was just to validate that his dots were actually fluorescing in the near infrared. So our device was never intended to actually size.
No, you just want to image.
Yeah.
There must be a correlation between the dot size, the intensity that it gives off, and your ability to image. I was just wondering if you explored that at all.
Yeah. One trouble is that the signal that we're actually detecting is the fluorescence from the dot. So we're not actually imaging the actual nanoparticle. but we're imaging the fluorescent signal that is going off.
Yeah, but it's still kind of, I get that. Okay. Did you look at other markets? Because this is a fascinating space. If you can actually do this, I think your low-hanging fruit for commercialization is not this market. I think the security market offers a real problem that needs to be solved, and the ability to place a discrete and unique marker that can be finished in the field.
Yeah, we'd love to talk to you about it after this.
Okay, anybody else have any questions or comments? Okay, we are at the end. I think we've seen a whole bunch of outstanding students who